Hello everyone, I'm Zhihao from Fudan University. Today, I'm glad to present our work, TyrLoc, a low-cost multi-technology MIMO localization system with a single IF chain. This is a joint work with my colleague Tai-Wei He, Junwei Yin, Professor Yue Dongxu, and Professor Junwu. Wireless indoor localization is playing a crucial role in many applications, such as operating robots in a warehouse, providing navigation services in an exhibition center, or helping you to find your car in a parking garage. Many efforts have been devoted to building localization systems based on commodity Wi-Fi devices, but it is still not enough. Accurate Wi-Fi localization attributes to the acquisition of channel state information, but only very few Wi-Fi cards can extract it by CSI tool. Besides, each technology has its own strengths and suitable scenarios. As for BLE and LoRa, there doesn't exist a commodity device that offers the public functionality of acquiring rich channel information. It restricts their localization accuracy. Hence, we advise to use low-cost SDR for multi-technology localization services. For AOA-based localization system, using a larger antenna array is an effective way to achieve better localization performance. So, we would like to build a new localization system. It employs a low-cost SDR to provide universal localization functionality, and use a large-scale array to improve localization performance. This table lists the performance parameters of popular software-defined radios. We can observe that the price differs significantly between the devices whether support MIMO or not. We choose the Bluetooth SDR as the receiving device, which is only equipped with single transmitting port and single receiving port. Then, the next question is how to extend the antenna array. If we synchronize multiple devices to connect more antennas, the price of the system will increase several-fold. A promising and low-cost approach is to employ an RF switch. Previous work taking this method requires an additional radio chain to connect the reference antenna, but most of low-cost SDRs only support single receiving port. Can we do that without a reference radio chain? Our solution is TyrLoc. The left figure shows the basic idea of TyrLoc. It only uses a single RF chain to build a virtual synchronous antenna array. The right figure is the hardware demonstration. The TyrLoc system consists of three low-cost components: the Bluetooth SDR, an FPGA board, and an RF switch. Bluetooth is a low-end SDR, which is only equipped with single RF chain. We modify its firmware to enable the MIMO functionality. We use the remaining logic resources of the FPGA chip in Bluetooth SDR to implement extra modules. The switch controller is designed to generate cyclic control signals of the RF switch. The unused GPIO ports of Bluetooth SDR is limited, so we implement a UART module to convert the parallel control signals into serial signals. The antenna tagger will tag the data from the ADC with antenna ID, so that we can easily distinguish the signals coming from different antennas. The FPGA board is used to recover the serial control signals to 3-bit parallel signals. It also can send the control commands to the switch controller. Finally, the RF switch will complete antenna switching according to the control signals. It can work at different switching frequency and pattern. In TyrLoc, we can use single RF chain to receive packets from different antennas. Here is an example. The ideal case is in each switching slot, the SDR can receive one packet. However, we can't directly group the signal phase of different antennas to construct an antenna array. The greatest challenge for TyrLoc is to eliminate the phase distortion caused by carrier frequency offset. Let's start with the impact of CFO on the phase of synchronous antenna array. If three synchronized RF chains are connected to three antennas, this is the signal phase of first estimation, second estimation, and third estimation. We can see that the phi theta is the relative phase difference between antennas. It is caused by the different propagation distance from the signal source to antennas. We can infer the angle of arrival through it. At the same time, we can observe that the absolute phase of the antenna drifts over time. This phase offset is caused by carrier frequency offset. For synchronous array, CFO doesn't distort AOA estimation because we only use the relative phase difference, phi theta. If we use an RF switch to receive signals from different antennas, we can only obtain the phase of one antenna in a single estimation. The relative phase difference is mixed with phi if. The phase distortion caused by CFO hinders us from directly grouping the phase of antenna array. The phase offset caused by CFO can be expressed as the left equation, so we need accurate CFO estimation. Then we can calculate the phase offset and calibrate it. Moore's algorithm is widely used for CFO estimation. Then I will introduce its basic idea. For Wi-Fi, the training sequence in the preamble is used to estimate CFO. It consists of two identical symbols. Moore's algorithm uses their multiplication to calculate the CFO. The variance at the range of the estimation is listed in the table. The traditional Moore's algorithm is used for communication purpose. It pursues extremely high time efficiency, while allows relatively large estimation variance. That does not influence packet reception but are detrimental to our AOA estimation. Then, how to improve the accuracy of CFO estimation? We can note that if we extend the time interval Ti, the variance of the CFO estimation will greatly decrease. We propose a two-stage logic to get fine-grained CFO estimation. In the first stage, we perform traditional Moore's algorithm on two neighboring training symbols in a packet. The time interval is T symbol. In the second stage, we perform the Moore's algorithm on two training sequences of adjacent packets. Now, the time interval is T packet. It is much larger than T symbol. So, we can significantly reduce the variance of CFO estimates by increasing the time interval. But the side effect is the decrease of estimation range. In TyrLoc, the initial CFO may be very large, which exceeds the estimation range of interpacket methods. Therefore, Moore's algorithm cannot be directly used to estimate the CFO across the packets received on different antennas. The basic idea of our solution is shown in the figure. In the first stage, we perform the intra-packet CFO estimation. The result is taken as the core CFO, and it is used to adjust the carrier frequency of Bluetooth SDR. Then, we can narrow down the carrier frequency gap between the transmitter and the receiver to satisfy the estimation range requirement. In the second stage, we perform the inter-packet CFO estimation. We also take the estimation result to further shrink the CFO, limited by the Bluetooth minimum adjustment step of carrier frequency and the instability of CFO. Residual CFO still exists, but at this time, we can obtain exact CFO estimates to calibrate the phase shift. A new problem is CFO is not constant over time as the oscillator slightly drifts, so we need to constantly estimate the CFO. In TyrLoc, the IDs of the antennas are numbered from 0 to 7. We call the antenna 0 the pivot antenna. The pivot antenna is the starting point in each round of switching. We use it to perform inter-packet CFO estimation. We have designed three switching patterns for TyrLoc. In pattern A, the pivot antenna only repeats once in a round to shorten the switching cycle as much as possible, so that we can speed up the location update rate. To improve the performance of CFO calibration, the pivot antenna repeats once for every antenna in pattern C. It's a trade-off between update rate and accuracy. If we use pattern C, the left figure illustrates the phases of the array. The blue dot is the phase of pivot antenna X0. Orange dot is the phase of antenna X1 to X7. Due to the instability of CFO, the slopes between every two adjacent blue points are slightly different. The red cycled is the phase of virtual pivot antenna X0'. It is predicted based on the CFO estimates. Delta phi I is the actual phase caused by the difference of propagation paths between X0 and Xi. Then, aligning all phase offset ΔPhi to the pivot antenna, we can construct a virtual synchronous antenna array. The next challenge is the AOA estimation of non-uniform array. Music with spatial smoothing is an effective way to estimate the angle of multipath signals accurately. But the spatial smoothing operation requires a uniform array. As shown in the figure, when switching to the antenna Xi, no valid packet received, possibly due to packet loss, no packet events, or the preamble is split by the RF switch. That will result in the absence of antenna Xi in the virtual array. Now, the virtual array is incomplete or non-uniform. Therefore, music with spatial smoothing doesn't work robustly. So, we employ the interpolated array transform to tackle this problem. It designs a mapping matrix to convert the non-uniform array data into the virtual uniform array data. That allows us to keep using the spatial smoothing approach. Due to the time is limited, you can refer to our paper to get more details about it. We evaluate the performance of TyrLoc in 2 rooms. The layouts of the rooms are shown in the figure. We tested the AOA micro benchmarks and the localization performance of Wi-Fi, BLE, and LoRa respectively. First, we evaluate the AOA estimation capability of TyrLoc. We use the music algorithm with spatial smoothing to estimate the arriving angle of the signal. The ground truth is calculated based on the physical locations of the transmitter and the TyrLoc. One can observe that LoRa can achieve higher AOA estimation accuracy. We also evaluate the localization performance in line-of-sight and non-line-of-sight scenarios. When the direct path signal is blocked, LoRa's performance slightly drops 25%, while the accuracy of Wi-Fi and BLE degrade by 52% and 72%. Due to the strong penetration ability of LoRa, it shows the great potential for localization in complex indoor environments. We further using TyrLoc to track the movement of a transmitter that is held in a person's hand. We ask a user to move the transmitter along the trajectory drawn on the ground to write letters. The trajectory M and O is obtained using Wi-Fi, B and I is tracked by BLE, and SYS is conducted by LoRa. We also compare TyrLoc with the localization system with synchronous antenna array. Compared with the array track system built with 2-WAP v3, TyrLoc enables a larger antenna array with much more lower cost and achieves higher localization accuracy. Compared with the SpotFi built with commodity Wi-Fi devices, TyrLoc is multifunctional and more flexible. It supports not only Wi-Fi but also BLE and LoRa-based localization services. Both of them are more accurate than Wi-Fi. Here is a short demo of real-time localization based on LoRa. The transmitter is a wireless stick equipped with a commodity LoRa chip. We use 2 Bluetooth SDR to capture the signals. In this demo, the transmitter is mounted on a tripod. Then, we hold the tripod in hand and walk in the room. The blue square R1 and R2 is the location of 2 receivers. Each of them is equipped with an 8-antenna array. TyrLoc captures the LoRa signals and calculates the locations of transmitter in real time. The blue line is the trajectory estimated by TyrLoc. Finally, let me summarize our work. TyrLoc uses a cheap SDR and enables a large-scale antenna array through a low-cost method that greatly reduces the cost of whole system. Benefiting from the flexibility of SDR, it is compatible with various wireless protocols and supports multi-technology localization services. To address the limitation of single RF chain, a novel method is proposed to calibrate the phase distortion caused by CFO. This technique is meaningful to other low-cost SDR with a single RF chain. That's all for today. Thank you for listening, and I'm happy to hear any questions from you.